Okay, so the next part here is, I think, very interesting and also extremely important to understanding all of probability. So there are two really fundamental theorems in statistics. It's the law of large numbers and the central limit theorem, and we've talked about. We haven't gotten to either of those yet in this course. They're both very important, but one that's but the most important concept in probability, or one of the most important concepts at least, is how do we construct a uniform 0-1 random variable? And the reason why it's so important will become apparent as we progress and we see some additional properties of random variables as it relates to the uniform distribution. Because what we'll see is that the uniform distribution is in fact fundamental to all of probability, to all of distributions that we see in probability. But before we get ahead of ourselves, and the uniform distribution is fundamental, and if we back up just one step, we'll see that the Bernoulli distribution, the Bernoulli 1/2, the distribution of a fair coin toss, is the most fundamental thing that actually plays a role in the entire development of probability theory. And that's through how we construct a uniform random variable. So we've been talking about random variables, continuous random variables, and in particular the uniform 0-1 random variable, as if it makes sense, right? So it makes sense to say I have a box of 10 things and I'm going to pick one out and they all have equal probability of being picked. So there's something there that makes intuitive sense because we can imagine doing it ourselves, right? We can imagine putting balls in a box, numbering them 1 to 10 and pulling one out and imagining that they're all equally likely to occur. We tried to get some intuition for the uniform 0-1 in the by showing up above how, or previously, how we would take some kind of limit, take a very large set, divide by n, take n to infinity, and so on. But that's still pretty abstract in terms of how we can see any relationship between concrete things that we can touch and feel and things and the uniform distribution. Here we're going to have a more concrete construction of the uniform 0-1. Okay, so what we're going to do is we're going to imagine tossing a coin, and we're going to actually generate a uniform random variable just by tossing a coin. Okay, so here's how we're going to do it. We're going to let I1, we're going to imagine tossing a coin indefinitely for as long as we want, but we can stop anytime. And we'll talk about that in a second too. But we have independent Bernoulli 1/2 random variables. Okay, so these are from, repeated tosses of a fair coin. So we're going to toss a coin repeatedly. And what we're going to do is we're going to define a random number as follows. So given that the values of these Bernoullis are I1, little I1, little I2, so these are zeros and ones, etc., we're going to define a random variable y to be the sum of these indicators, these random indicators, weighted by 2 to the minus j. So how this works is, how this ends up working is Y has a dyadic, what's called a dyadic expansion. Which is a base 2 expansion where we expand we expand the value, we expand it in a binary sense, okay? And what we're doing here is we have, let's say, j equals 1. Let me set this up actually. So we have j equals 1, j equals 2, 3, 4, and so on indefinitely. And what we're doing is we are splitting the unit interval in half. Well, we're splitting into finer and finer partitions, and we're saying, and we're tossing a coin at each step, and we're saying if it's 0, if it's heads, we're going to take the right side of the partition. If it's tails, we're going to take the left side. So at j equals 1, we're just deciding, is the number bigger than a half? Is it less than a half? And of course, for a uniform 0, 1, that should be half, half. And in the case that we're talking about, it's half, half, because we toss a heads with probably a half, we toss a tails with probably a half. When we toss the next one, we're determining, okay, which quarter are we in? So let's say, let's play this out, and let's suppose that we have, we've tossed head, tail, tail, head, tail. Okay. No, I guess I should do it this way. Head, tail, tail, head, tail. So we determined the head, so we're going to be in the big part of we're going to be on the right side. Okay. Well, now once we're in the right side, we're going to say, are we in the left side of that sub piece or on the right side? If we toss a head, we stay on the right side. If we toss a tail, we're on the left side. So here we toss the tail. And then we continue recursively like this. So we refine. We refine the subinterval that we're in again. And we tossed another tail, so we're going to be on the left side of that. And then we're going to refine that subinterval again. And this time we tossed a head, so we're going to be on the right side of that. And then we're going to refine that piece. And this time we tossed a tail, so we'll be on the left side, and so on. And so as we continue, we're going to recursively narrow down where we are until we're pinned. Theoretically, in the limit, we're pinned, and it's actually uniquely determining a real number. And so this is theoretically how we think about constructing a uniform 0, 1 random variable, and we can do it within a particular accuracy. So we could generate U from a uniform to within 2 to the minus n accuracy by tossing a coin n times and defining U, call it U tilde, to be the sum from j equals 1 to n, 2 to the minus j indicator of j. So when we cut this sum off, of course, we can't actually in real life toss a coin infinitely many times. Well, the best we can do is toss it as many times as we have time to do, and as we can do. But what this is saying is that we can actually achieve, in principle, we can achieve whatever level of accuracy we want, as long as we toss the coin enough times, and it tells us exactly how many times we have to toss it to get that level of accuracy. Okay, so this is a very important and very fundamental concept. It's something that will potentially be useful in proving certain properties of random variables. Conceptually, it's also important to understand where the uniform random variable comes from, because there's something called a transformation theorem later on, which allows us to actually generate a copy of any random variable, provided that we have a copy of a uniform random variable. So this is the last part that we're going to talk specifically about uniform 0-1s for the moment. And then in the next video, we'll talk about the Gaussian distribution.